in an extreme type of analogy, there are folk who think that the real universe that we see, that we are part of, is a result of fluctuation of matter and antimatter, and somehow that imbalance allows this material universe to exist. So that's what I want to say about that. So you can spend much time understanding these systems. So thank you for that.
So you guys have no real physical understanding of why nanoparticles enhance those particular properties?
Not really. Not that we can, we can do a lot of supposition. Obviously, it must be surface effects. There has to be, because surface to volume ratio is much higher with nanoparticles than with regular type system. If you compare a nanospherical particle with a basketball, the volume dominates for a basketball, a baseball. But as you pare the system down much smaller, down to the size of a marble, right? The surface area now begins to speak louder than the volume aspect of it. So obviously it has to do something with surface in all probability. It probably has that where the silver particles are finding themselves in this matrix, as they say. For me, I'm an old-time physicist. I don't think you really know it until you can work the mathematics out.
So is there any research, maybe other facilities?
Oh yeah, I think folk are working to their model. Generally, you get after this by modeling it. I'm sure that my pictures are better than there are folks who are probably modeling, and they're seeing how if you change one something, you get this outcome, and you get a handle on the physics. You see, so this now becomes not a simple deterministic problem. It's obviously a statistical problem because you have so many different particles until all this work and no questions.
Noise, of course, is a very important topic for experimentalists, because some theoretician might tell you that I want to detect 1 atom at a distance of 1 mile, and you can do it on paper, okay? But the atom is emitting light, so why can't you detect 1 atom at a distance of 1 mile? The only thing that prevents you from doing it is the noise, okay? What you can do as an experimentalist depends on how much you can suppress the noise. That's an extremely important.
So is it a lot more cost effective to produce the dope films than the crystal films?
We just decided to go in the lab and make these films, and it doesn't take. We could generate a whole set of films in a week's time. Now, Dr. Agarwal, growing your crystals. I guess you can dig, huh?
How long would it take for him to grow?
Yeah, growing crystal is very long process. It is like stacking atoms.
Yeah, so you got to stack them slowly.
In 1 gram, you have 10 to the power 23 atoms. Now you go to stack yourself.
That's why it takes so long.
Yeah, because they got to sit in the right place. They got to be stacked according to the geographical structure of that particular crystal type. So it takes time for them to organize themselves and getting the right slot.
I was wondering, is there a measurement of D star? If you embed this silver nanoparticle, has anyone measured that D star goes up?
Oh, I'm not sure. We may need to. No, I do not know if D star has been measured with these nanoparticles, because that was not what we were trying to do. But that may be something that we possibly
So the
can.
figure of merit,
Yes, sir.
short figure of merit is higher.
Yes.
Higher in the silver
Yes.
particles of silver
What does
nanoparticles.
figure of merit measure?
Figure of merit is it can be either a voltage figure of merit or it can be figure of merit is actually how much
Is that related to D star?
Some of them are. There are different figures of merit. Generally, the fact is that D star itself is considered to be a figure of merit. And I guess we may need to look in
I'm
to
sure the
see.
D star will be higher.
Yeah, it will be
The
higher.
D star is a calculated number.
But it is calculated and you can get the ideal D star. But you can measure D star for these units.
So those plots that you see for D star, they are calculated.
D star is a calculated.
Well, you can measure it. It is measurable.
But you are measuring certain quantities.
So these are all theoretical plots?
These are not theoretical. They are experimental data with the bioelectric coefficient, electric constant, and all that. You saw those.
This one right here would be the ideal. You see, do you see that there line there? That is a calculated D star. And none of these true ones can get as high as this. Okay, so this is like a Carnot engine in thermal. The best engine is a Carnot engine. So the best that you can get with D star is that curve right there. And the true experimental ones are always less than
You
that
can
high.
see here that the bioelectric detectors have straight bandwidth.
Where are
They
you?
are
Where are you, Dr. Lyle?
10 power radiation thermocouples.
Yeah. Oh, yes.
Those are
there.
all straight. Straight. So they are operable in a very wide range of wavelength as compared to mercury. Cadmium telluride or mercury, you see that the curve falls right away.
Yeah.
So they are good.
They're
up to a certain
good,
wavelength.
but they're
As soon as
low
you go beyond
in D
that,
star.
then it goes down. But initially at room temperature, it's 2 orders of magnitude higher. 10 power 10, 9, or 10 power 11. EGS is right there. Thermocouples and radiation thermocouples. Straight line, Rolex hands and all that. EGS is there.
Let me mention one other thing about signal to noise ratio. Dr. Sharma mentioned. If the signal to, you always want the signal to noise ratio to be greater than 1 for your system. The lower limit that where you can measure something is when the signal noise ratio is equal to 1. If it's less than 1, then you're trying to look at there's too much noise. You cannot pull it out of the system without doing some other kinds of processing the data. You can do what are called auto correlation functions, and you can pull the signal out of noise. But that's another set of can of worms that become software action to find the signal in a bunch of noise. But if you can set your electronics up so that the signal to noise ratio is larger anyway than 1, you're better off from the beginning.
I think the thin film studies have not been done. I'm sure I don't think weird. As a function of the thickness of the film.
No, we have not done that.
That is pretty tough. So there has to be a thickness. Like you go from a thin film to a thick film
Yes.
regime,
Yes.
and where the properties changes.
So there's lots of physics
Yeah.
still to be done on
That's
these.
why these topics are lasting from last. That's why when I said in the morning that the TDS literature, but there is a maximum literature. TDS, we put the TDS in the room
maybe another thing one should mention is that the human eye is probably one of the best detectors.
Over a very large bandwidth.
Yes, yes. And if you are in a very dark room, I mean, you can see something like 3 or 4 photons per second.
One of the physics at A&M probably in the middle of computer intelligence. If you look at the Pune paper published in thermal detectors, I think the percentage wise is pretty high. On one lab.
One lab.
One lab.
Okay, well, if there are no other questions, let's thank Mr. Jim. Are you another speaker?
Oh yeah, they're great. Yeah, there's lots of information there, and you know what I'm saying. I make sure to give them some where you are. Oh yeah.
That's what she did, but I can give you my example.
Oh yeah. Claudia.
I get the software.
Okay. Sadia Smith. I thought Sadia Smith. This is great. Are you
want to get a coffee? Looks like you're sleepy, right? I got like.
You will start here. Okay. Great. And, so you said from Dresden, right down the street. So you're going to, do you have a BSK document? No, I got this here. I got one. Yeah. But so have you graduated yet? Or you get a BS or a master's? You are in BS first now, and then we just keep. You understand what I'm saying? We just keep the whole time. But they do good work over there. And the CIM, all that's other business. Might as well, because you know, I'm a the only difference between what I have is the sound. You understand what I'm saying? It's all the same. If you got the feel of the instrument in your hand, you can tell, you know what I mean, the microphones. So there's really no difference other than it's more accurate. It costs more. You don't want to break it down. But still, once you get your hands around it and understand, it's just something that you learn. That's what You mean over at the CI? Yes, because what happens when you work on it and you set it to the side, you know what I'm saying, and it starts gathering dust. But once you take an interest in it, you can bring all this little piece of equipment back to life. You understand what I mean? You can go down and just find equipment sitting on the desk. Some student has probably already gotten his master's or PhD using that system, but now no one's working on it, so it's just sitting to the side. But if you choose to show an interest in it, then you can see, okay, what do I need to do? Like even some of those old
I forgot this stuff.